Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Morales. Thanks for meeting me during your office hours. I wanted to get your advice on designing a catalyst for my green chemistry project.
Hello, Daniel, of course. Tell me where you are in the project and what specific green goals you have for the catalyst.
I want to accelerate a biomass conversion reaction to produce a platform chemical while minimizing hazardous solvents and avoiding toxic metal residues. I am considering between a heterogeneous metal catalyst, an organocatalyst, and an immobilized enzyme.
That is a good comparison. Each approach has trade-offs. Heterogeneous catalysts, like supported nanoparticles, are easy to recover and reuse, which reduces waste. Organocatalysts avoid transition metal contamination and are attractive for pharmaceutical-grade products. Enzymes operate under mild conditions and are very selective.
When you say supported nanoparticles are easy to recover, do you mean we can filter the catalyst out and run the reaction again without regenerating it?
Yes, exactly. A catalyst on a solid support, such as silica or a polymer, can be separated by filtration or by using a continuous flow reactor. That cuts down solvent waste because you do not need extensive extraction steps to remove dissolved catalysts.
I have read about metal organic frameworks as supports. How do they compare with traditional supports in green applications?
Metal organic frameworks provide high surface area and tunable pores. They can enhance mass transport and sometimes protect active sites from deactivation. They also allow immobilization of enzymes while preserving activity. If we can immobilize an enzyme on a metal organic framework, we get both activity and recyclability without harsh solvents.
That idea of a mobilized enzyme sounds promising. But are enzymes robust enough for industrial conditions?
Enzymes can be engineered for stability, and immobilization itself often increases thermal and operational stability. In biodiesel production, for example, lipases are used to transesterify oils under mild temperatures and with far less chemical waste than conventional base catalysis.
So enzyme catalysis improves selectivity and reduces hazardous byproducts. What about organocatalysis for pharmaceutical intermediates?
Organocatalysis uses small organic molecules as catalysts. A major green advantage is elimination of transition metals that can contaminate APIs. Organocatalysts also often work at ambient conditions and can provide excellent stereo control, which increases atom economy and reduces the need for additional purification.
You mentioned photocatalysis earlier in the seminar. Can photocatalysts be considered green if they involve rare metals?
Good question. Photocatalysis can be green when it uses abundant materials and visible light. Organic photocatalysts and graphitic carbon nitride are examples that avoid rare metals. The key is choosing photoactive materials that are non-toxic and can be reused, or using solar light to minimize energy input.
Would electrocatalysis fit into my project? I could couple biomass conversion with an electrochemical cell to drive a step without high temperature.
Electrocatalysis is an excellent green strategy when electricity comes from renewable sources. It often allows precise control of redox steps and can operate at ambient temperature and pressure. Still, you must consider electrode stability and catalyst poisoning.
I am also worried about scale-up from bench to pilot plant. Which catalytic approach typically scales best while keeping green metrics high?
Heterogeneous catalysts and flow reactors tend to scale well because catalysts are recoverable and heat and mass transfer are easier to manage in continuous systems. Biocatalysis can scale too, but it often requires careful control of conditions and sometimes immobilization strategies to be economically viable.
Can you give a concrete case study that combines catalysis and green chemistry principles?
Certainly. One example is the conversion of furfural from agricultural waste into furfural alcohol using a supported noble metal catalyst under hydrogen at modest pressure. By using a recyclable supported catalyst and solvent that is renewable or benign, mass efficiency and environmental impact improve relative to older batch methods.
Are there examples where organocatalysis replaced metal catalysis and drug synthesis to meet green standards?
Yes, several pharmaceutical companies now use organocatalytic steps to avoid metal trace removal. In one case, an enantioselective aldol reaction moved from a chiral metal complex to an organocatalyst. That reduced heavy metal wastes and simplified purification, improving the overall E factor.
You mentioned E factor, which measures waste. How does catalysis influence E factor practically?
Efficient catalysts increase yield and selectivity, reduce side products, and often allow milder conditions. That lowers solvent use and reagent excess. Recyclable catalysts cut down on catalyst waste, which all reduce the E factor.
What about catalyst toxicity and lifecycle? How do we evaluate if a catalyst is truly green?
We must consider the whole life cycle. That includes raw material sourcing for the catalyst, energy required to prepare it, its operational lifetime, recyclability, and disposal. A catalyst that uses abundant elements, can be prepared with less energy, and is highly recyclable scores better on green metrics.
I'm deciding between starting with an organocatalyst screen or testing immobilized enzymes on MOF supports. Which would you recommend for achieving rapid progress in a thesis timeline?
For faster initial results, organocatalyst screening may be quicker since you can run small-scale screens in parallel without complex immobilization steps. If your target reaction needs exceptional regio or enantioselectivity, organocatalysis might give faster leads. However, for long-term sustainability and industrial relevance, demonstrating an immobilized enzyme on a MOF would make a strong contribution.
That helps. I think I will start with organocatalyst screening while setting up collaborations to try enzyme immobilization later.
That sounds like a balanced plan. Keep careful metrics on solvent use, catalyst loading, turnover number, and recyclability as you test. Those data will show the green benefits of your chosen approach.
Thank you. I will prepare a screening plan and a list of metrics to measure. Can we review it next week?
Yes. Bring your proposed catalysts, expected reaction conditions, and how you will measure recyclability. We can refine the plan and discuss potential MOF partners.
Great. I appreciate your guidance on catalysis in green chemistry.
You are welcome. I look forward to seeing your results.
Listen again to part of the conversation, then answer the question.
If we can immobilize an enzyme on a metal organic framework, we get both activity and recyclability without harsh solvents.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.